Hello students, welcome to EPG Pathshala. I am Dr. Ajit Kumar Mahapatra from the Department of Physics and Astrophysics, University of Delhi, Delhi, India. Today we are going to talk on module Birefringence. It comes in the subject Nonlinear Optics under the paper Characterization of Materials Part 2. After completing this module, the students will be able to understand the second harmonic generation and the introduction to it, and the details of phase matching and what is birefringence. The second harmonic generation, also called frequency doubling and abbreviated as HHG, is a nonlinear optical process in which photons with same frequencies interact with a nonlinear material combined to generate new photons with twice the energy and then twice the frequency and half the wavelength of the initial photons. Here, the dipoles oscillating with the applied electric field of frequency omega radiates electric field with frequency 2 omega as well as omega. In second harmonic generation, the applied and driving fields at frequency omega produces nonlinear polarization at frequency 2 omega. The total second harmonic generation field generated at point R is the resultant sum of interfering waves generated between the edge of medium R is equal to 0 and R is given as E2 is directly proportional to epsilon 0 chi 2 E1 square omega 2 square e to the power 2I multiplied by K2 R minus omega 2 t whole integration of 0 to R e to the power I to K1 minus K2 times R0 dR0, which is equal to epsilon 0 chi 2 E1 square omega 2 square e to the power 2I times K2R minus omega 2 t multiplied by e to the power I to K1 minus K2 times R0 whole divided by I times 2K1 minus K2. The second harmonic generation frequency omega 2 and wave vector K2 is related to the wave vector and frequency K1 and omega 1 of the fundamental by K1 is equal to N1 omega 1 divided by C, K2 is equal to N2 omega 2 divided by C, and omega 2 is equal to 2 omega 1. That implies K2 is equal to 2 N2 omega 1 divided by C, where N1 and N2 are the refractive indices of the medium at frequencies omega 1 and omega 2 respectively. Phase matching. The phase matching of the radiated electric field of frequency omega and omega 2 is critical in second harmonic generation. They have to be in phase to favor constructive interference, and the applied electric field should be strong enough to generate the second order radiation, but not so strong that the first order term dominates. So, we could think of second harmonic generation signal as a perturbation, and the lights of two frequencies should be added and should not cancel each other. Considering the wave propagation in the plus z direction, the total output is sum or the integration of the all dipoles at every position in the material. Here eta is equal to 1 by L square multiplied by integration of 0 to L e to the power 2 kx z e to the power minus ikx z dz whole square, which is equal to 1 by L square times integration of 0 to L e to the power I k z dz whole square, which is equal to sine of delta k L divided by 2 whole divided by delta k L divided by 2 whole square. And the second harmonic intensity at z can be expressed as I 2 omega, the function of z, is directly proportional to I omega square 0 multiplied by sine of delta k dot z divided by 2 whole divided by delta k z by 2 whole square, where I omega 0 is the incident intensity. So, the maximum intensity is achieved for identical phases. This function has a maximum for delta k dot z is equal to 0 and 0 for delta k times z is equal to 2n pi, indicating that the condition for most efficient SHG is delta k is equal to 0 and is termed as phase matching. The output of equations 3 and 4 is a sine C function given by sine C multiplied by delta k L divided by 2 is equal to sine of delta k L divided by 2 whole divided by delta k L by 2 whole square. Many phase sensitive nonlinear processes, especially the parametric processes including frequency doubling, sum and difference frequency generation, and parametric amplification and oscillation, require phase matching to be efficient. For optimum nonlinear frequency conversion, it is required to have proper phase relationship between the interacting waves maintained along the propagation direction. This condition is fulfilled when the amplitudes from different locations are all in phase with the resultant total wave at the end of the nonlinear crystal. An effective nonlinear interaction is possible with phase mismatch close to 0. The phase matching of frequency doubling is given by delta k is equal to 2 k1 minus k2 is equal to 0, where k1 and k2 are the wave numbers of the fundamental and second harmonic beam respectively. Without chromatic dispersion, k2 is equal to 2 k1 would hold, so that the phase mismatch vanishes. In figure 1, the arrows indicate the phase corresponding to the amplitude contributions from different parts of the nonlinear crystal to the harmonic wave. These contributions aided constructively only when the phase matching is achieved and results high power conversion efficiency. Else, the direction of energy transfer changes periodically with the change in phase between the interacting waves during passaging through the crystal. The energy then oscillates between the waves without being transferred in a constant direction. The effect on the second harmonic power conversion in a crystal along the propagation direction is demonstrated in figure 2. Here, the solid curve is observed during phase matching that indicates growth of power proportional to the square of the propagation distance. The dashed curve represents the power during non-phase matching, with the second harmonic power oscillating between 0 and a small value. Effect of temperature in the SSG power efficiency. The crystal temperature around the optimum point develops phase mismatch and variation in the conversion efficiency. Figure 3 plots the second harmonic power versus temperature deviation from the optimum point with homogeneous temperature distribution in a crystal. The high conversion efficiency is inversely proportional to the crystal length and also relies on the temperature dependence of the refractive indices involved. Similar relations apply to other nonlinear frequency conversion processes. Similar curves are obtained, such as for critical phase matching, when the angular orientation of the crystal is varied. The second harmonic power versus temperature deviation from the optimum point with homogeneous temperature distribution in a crystal is shown in the figure. In practice, the phase matching curve is not as symmetric as shown in the figure. For example, it becomes asymmetric if the crystal temperature is not homogeneously distributed throughout the length or lower in temperature values at the end faces compared to the middle of the crystal. The temperature homogeneity in a crystal could be quantified from the phase matching curve, and the conversion efficiency could be optimized by fabricating crystals of desirable dimension. Now, let's discuss about the coherence length. The oscillations caused by interference between the second harmonic generation waves generated at different points along the path severely limits the SSG intensity unless the phase matching conditions of delta k is equal to 2k1 minus k2 is equal to 0, and the index matching is n1 omega 1 is equal to n2 omega 2 are fulfilled in equivalent conditions. As most of the optical media are dispersive, n1 is not equal to n2. Here, the delta k is equal to 2k1 minus k2, which is not equal to 0. Hence, the SSG amplitude oscillates as e to the power I 2k1 minus k2 r with periodicity as Lc is equal to pi divided by 2k1 minus k2 along the path. The distance, this Lc, is called coherence length and is typically several wavelengths in condensed medium. In a SSG medium, the coherence length is infinite and it satisfies the phase or index matching, and it leads to complete conversion of fundamental into the SH. Efficient second harmonic generation requires phase matching or momentum conservation, satisfying the index matching of n1 omega 1 is equal to n2 times 2 omega 1. The difficulty in materials is that they are usually dispersive and the refractive index increases with frequency with n2 is greater than n1 in normal dispersion. Phase matching techniques. The chromatic dispersion of an optical medium is the phenomenon where the phase velocity and group velocity of light propagating in a medium depend on the optical frequency. Absence of chromatic dispersion could lead to K2 is equal to 2K1 and the phase mismatch vanishes. Due to chromatic dispersion, the wave number of the second harmonic is larger than twice of the fundamental wave. Dispersion generally causes a non-zero phase mismatch as shown in figure 4. Special measures could be taken to avoid this by choosing a different polarization in a birefringent crystal. Now let us see what exactly the birefringence means. The most common technique for achieving phase matching is the natural birefringence or double refraction of uniaxial anisotropic crystals. Birefringence is a property of non-isotropic material with refractive index dependence on the polarization direction, that is, the direction of the electric field, favoring the material capable of exhibiting double refraction by shining an unpolarized light beam. It is referred as the double refraction of light in a transparent molecularly ordered material manifested by the existence of orientation dependent differences in refractive index. These optically anisotropic materials with directionally dependent property are termed as birefringent. The birefringence could be quantified as the maximum difference between the refractive indices of the material. Crystals with asymmetric crystal structures are often birefringent. Now, the isotropic and anisotropic materials. Optically isotropic materials have the properties of identical refractive index in all directions throughout the crystalline lattice. Examples of isotropic solids are glass, table salt which is sodium chloride, polymers and a wide variety of both organic and inorganic compounds. The isotropic properties remain symmetrical regardless of the direction of measurement, with each type of probe providing identical results. The term anisotropy refers to a non-uniform spatial distribution of properties resulting for sample materials probed from various directions within the same material. Generally, the observed properties are dependent on the particular probe being used and often very dependent on the phenomena for optical, acoustical, thermal, magnetic or electrical events. Generally, the anisotropic crystals such as quartz, calcite and tourmaline have crystallographically distinct axes and interact with light by a mechanism that depends on the orientation of the crystalline lattice with respect to the incident light angle. Double refraction. When an unpolarized light beam is incident on a calcite crystal, it usually splits up into two linearly polarized beams. The beam which travels underived, delete undeviated, is known as the ordinary ray or O ray and obeys Snell's law of refraction. The second one doesn't obey Snell's law and is known as the extraordinary ray or E ray. Figure 5 represents the schematic diagram for the polarization of light by double refraction. The appearance of two beams is due to double refraction, and a crystal like calcite is referred as a double refracting crystal. The velocity of the O ray is same in all directions. The velocity of E ray is different in different direction. A substance like quartz or calcite that exhibits different properties in different directions is called an isotropic substance. The axis along which the two velocities are equal is known as the optic axis of crystal. In a crystal like calcite, two rays have the same speed only along the direction. Such crystals are known as uniaxial crystals. Here, nu 0 is equal to C by N0 and nu ER is equal to sin square theta divided by C by NE square plus cos square theta divided by C by N0 square for E ray, where NE and N0 are constant of the crystal and theta is the angle with the optic axis. C by NE and C divided by N0 are the velocities of the E ray when it propagates parallel and perpendicular to the optic axis respectively. Types of birefringent crystals. First one is uniaxial crystals. The simplest type of birefringence could be described as uniaxial, where the optical anisotropy is exhibited in a single and all directions perpendicular to it or at a given angle to it are optically equivalent. When the material is rotated around this axis, the optical behavior remains same. This special direction is termed as the optic axis of the material. The ordinary ray will also experience a refractive index N0, where the refractive index of the extraordinary ray could be between N0 and Ne, depending on the ray direction as described by the index ellipsoid. The magnitude of the difference delta n is equal to Ne minus N0 is quantified by the birefringence. The second one is biaxial materials. Biaxial crystals are somewhat complex and are characterized by three refractive indices corresponding to three principal axes of the crystal. For most ray directions, both the polarizations would be classified as extraordinary rays, but the different effective refractive indices. Being extraordinary waves, the direction of power flow is not identical to the direction of the wave vector in either case. The two refractive indices can be determined using the index ellipsoids for given directions of the polarization. For biaxial crystals, the index ellipsoid will not be an ellipsoid of revolution or spheroid, but is described by three unequal principal refractive indices with values n alpha, n beta and n gamma. Thus, there is no axis around which a rotation leaves the optical properties invariant, and observed in uniaxial crystal whose index ellipsoid is a spheroid. Different categories of birefringence. Birefringence is an inherent property of many anisotropic crystals including calcite and quartz, or it can also arise from other factors such as structural ordering, physical stress, deformation and strain. The naturally occurring materials with asymmetric in direction dependent refractive indexes are referred to have intrinsic birefringence. These materials include many anisotropic natural and synthetic crystals, minerals and chemicals. Structural birefringence is used to identify a wide spectrum of anisotropic formation including biological macromolecular assemblies such as chromosomes, muscle fibers, microtubules, liquid crystalline DNA and fibrous protein structures including in hair. Unlike many other forms, the structural birefringence is sensitive to the refractive index fluctuations or gradients present in the surrounding medium. The synthetic materials including fibers, long chain polymers and composites exhibit structural birefringence. Stress and strain birefringence arises when the external forces of deformations act on materials that are not intrinsic birefringent. For example, stretched films and fibers, deformed glasses and plastic lenses, and stressed polymer castings. In a naturally isotropic medium, birefringence can be induced by inhomogeneous mechanical stress. This can be observed by placing a piece of acrylic between two crossed polarizers and applying stress to the acrylic. Colored patterns could be observed resulting from the wavelength dependent effect of stress induced birefringence. Generally, the optical fibers are not birefringent, but some birefringence can result from bending that causes bend losses and from random perturbations as observed in bent optical fibers, and also due to thermal effects in laser crystals, which can lead to depolarization loss. Floor birefringence is the one that occurs due to induced alignment of materials such as asymmetric polymers that become ordered in presence of fluid flow. Rod-shaped and plate-like molecules and macromolecular assemblies such as high molecular weight DNA and detergents are often utilized as candidate in flow birefringent studies. Examples of birefringence. The phenomenon of birefringence occurs in non-isotropic crystals and below are few examples. In laser crystals such as vanadate or tungsten crystals belong to intrinsic birefrigerant. This is helpful in observing a linearly polarized output without depolarization loss. The nonlinear crystals for nonlinear frequency conversion are birefrigerant. Birefrigerant crystals are also used for making polarizers. Straight optical fibers exhibit a small degree of random birefrigerance which can disturb the polarization state of guided light over propagation distance. There are polarization maintaining fibers with strong artificial birefrigerants and are used for suppressing such effects. Quantification of birefrigerants. The magnitude of birefrigerants can be estimated in various ways. First, in ball crystals, the difference of refractive indices for the two polarization directions is considered to provide birefrigerance. Second, in optical fibers and other waveguides, the difference of effective refractive indices provide more appropriate to consider. This can be directly estimated from the difference in imaginary values of the propagation constants. Third, in a waveguide, if the waves with different polarization directions propagate together, their phase relation could be restored after integer multiples of the propagation beam length IP is equal to 2 pi divided by difference of the propagation constants. So students, let us now summarize what we have learned in this module. The efficiency of nonlinear optical processes could be determined from the nonlinear susceptibility of the medium and the phase mismatch parameter. To achieve optical energy conversion efficiency, the phase matching condition delta K should be equal to 2K1 minus K2 is equal to 0 has to be fulfilled. These relations can be translated into relations between the refractive indices at the respective frequencies. For example, in case of second harmonic generation, phase matching requires N1 omega 1 is equal to N2 and omega 2 is equal to 2 omega 1. Except for very specific cases, material dispersion usually does not allow to fulfill such kind of relations. The most commonly used technique of phase matching relies on utilizing birefrigerance. Birefrigerance is a phenomenon manifested by an asymmetric of properties that may be optical, electrical, mechanical, acoustical or magnetic in nature. A wide spectrum of materials display varying degrees of birefrigerance, but the ones of specific interest to the optical microscopist are those specimens that are transparent and readily observed in polarized lights. Thank you.